Hello and welcome. This video is specially useful to solve the FIR filter designing examples in academic curriculum. Here we are discussing the variation in the designing statement and how we can fit it to the designing steps which we discussed in the previous video. Always the designing statement specifies the frequency domain specification of the desired filter for which we are designing the filter, means finding the h of n for that specified frequency specification. So statement is design a digital FIR filter for the following specification. The specifications can be given in two different ways. It can be given magnitude spectrum of HD e raised to j omega, or HD e raised to j omega can be given in a complex form. When it is given in a magnitude form, magnitude of HD e raised to j omega is always 1 for the pass band. Here it is low pass filter, but it can be high pass filter, band pass filter. According to that, this frequency range changes. But for the pass band, the magnitude is always 1. And when HD e raised to j omega has mentioned in a complex form, it is m magnitude e raised to minus j m minus 1 by 2 omega. This m represent order of the filter and this m represent magnitude of the filter. So magnitude is always 1 and phase is m minus 1 by 2 omega. And this term is constant. Phase is always linear with the omega. For example, HD e raised to j omega is magnitude is 1 e raised to minus j 2 omega, where this m magnitude is 1, then this 2 represent 2 omega represent minus 2 omega represent phase. So m minus 1 by 2 is 2. That's why the order of the filter is 5. In the next step, when we are finding the HD e raised to j omega for given desired frequency response, we are applying the inverse Fourier transform. And when you are finding the inverse Fourier transform, the question is in HD e raised to j omega, if you are putting the magnitude and if you are putting the complex form, what is the solution? In both the case, you will get the sync pulse. The difference is when you are putting the magnitude value 1, you will get the sync pulse which is infinite in duration and non-causal. So when you are making it causal, you have to add the shift, and to make it finite, you have to multiply by the window function. And when you are putting the complex form e raised to minus j m minus 1 by 2 omega in place of the inverse Fourier transform HD e raised to j omega, the signal which we will get is the sync pulse, but it is already shifted by m minus 1 by 2. So in the next step, when you are following the next step, there is no need to add the shift as it is already shifted, it is already causal, only you have to make it finite by multiplying the window function. Let's see and how the shift is already added. H of n is the sequence. If its Fourier transform is h of omega, and if we multiply the h of omega with e raised to minus j n0 omega, what is the effect in the time domain? The shift get added by n0 unit in the time domain. So same thing happen here. In frequency domain, amplitude is 1 h of omega. If we multiply this h of omega amplitude 1 by e raised to minus j, this is n0 over omega. What will happen in the time domain? Time domain sequence is hdn. You will get the same shift in the time domain. So this is the time shifting property of Fourier transform. Due to that, if our HD omega is represented in a complex form, you will already get HDN shifted by m minus 1 by 2 due to the time shifting property of Fourier transform. That's why in the next step, you have to skip the adding the shift step. You can directly multiply by window function when you are using the complex form in a Fourier transform. Just let me demonstrate. This HDN you will get when you are putting the magnitude 1. And if you are putting the HD e raised to j omega in a complex form, you will get the HDN sync pulse, but it is shifted. That is the difference. Easiest way to find the HDN is you can directly use the generalized formula. Instead of solving the integration of Fourier transform, inverse Fourier transform, you can directly use the generalized formula for representing the HDN to reduce the computational complexity, or you can say reduce the designing time. The generalized formula which already discussed, sine of highest omega c of the passband minus sine of lowest omega c of the passband divided by pi n for n not equal to tau. Tau is m minus 1 by 2. And for n is equal to tau, highest frequency of passband minus lowest frequency of passband divided by pi. Let's see with the example. This is your HD e raised to j omega. The passband cutoff frequency is 0.4 pi to pi. This represents high pass filtering as all the high frequencies pass and the low frequencies suppressed. The amplitude is 0 for the low frequency. Now we'll fit this in the formula, sine of highest cutoff frequency of passband. So highest cutoff frequency is pi minus sine of lowest cutoff frequency is 0.4 pi divided by pi n. And here sine of, here not sine of, just highest frequency of passband is pi minus lowest frequency of passband is 0.4 pi divided by pi. For n is equal to m minus 1 by 2. If m is 5, this tau becomes 2. So this is the example. One more example we'll see. Design bandpass filter having passband frequency in the range 1 to 2 radian using Hanning window with m is equal to 5. So let us plot it first. This is a bandpass filter and its range of the passband is 1 to 2 radian. Now let's put this graph in our standard generalized formula to get the HDN. Sine of highest omega c of the passband is 2n minus sine of lowest omega c of passband 1. So sine of 1n divided by pi n for n is not equal to tau. Tau is m minus 1 by 2. M is 5 here. Then second, for n is equal to tau, highest frequency of passband is 2 minus lowest frequency of passband is 1 divided by pi is equal to 1 upon pi for n is equal to tau, that is 2. So instead of solving the integration of inverse Fourier transform, you can directly use the generalized form of HDN. Next variation in the designing statement. Design a digital low-pass FIR filter with the passband gain unity and the cutoff frequency is 1 kHz. Here the frequency is mentioned in hertz, cycles per second. In the previous example, it is mentioned in radian, omega. So cutoff frequency is 1 kHz and the sampling frequency is 5 kHz. The length of the impulse response should be 7. Use the rectangular window. Now in this low pass FIR filter, the cutoff frequency is mentioned in cycles per second. The length of the window is given 7, means the order of the filter m is equal to 7 and we are using rectangular window. First step is the given frequencies. This is the cutoff frequency of passband 1 kHz, sampling frequency 5 kHz. These frequencies are mentioned in cycles per second and the order of the filter is given here, m is equal to 7. Our first step, the above frequencies first we have to represent in terms of normalized frequency, and for that the normalized frequency omega c is equal to 2 pi fc by fs. Fc is 1 kHz and fs is the sampling frequency. Put the values and when we will solve we will get 2 by 5 pi, that is 0.4 pi. At this point, we can write the mathematical expression for the given low pass filter with its desired frequency specification. And it is HD e raised to j omega is equal to e raised to minus j m minus 1 by 2. M is 7, 7 minus 1 by 2, that is 3 omega. For the frequency range, it is a low pass filter and its cutoff frequency in a normalized form is 0.4 pi. That's why 0 to 0.4 pi, and otherwise it is 0 for the other frequencies. So this is the mathematical representation. Amplitude is 1. We can represent in a mod HD e raised to j omega also. Mod HD e raised to j omega is equal to 1 for the pass band, 0 to 0.4 pi. Otherwise it is 0. So this is the variation when the frequencies are given in a hertz cycle per second. We have to convert it into the radian per second, and then you can solve and you can follow the steps which we discussed in a filter designing. And this is the answer. You can try this, and this is the answer h of n which you are getting with the rectangular window for this desired frequency specification of low pass filter. Once you understand the variations in the designing statement, in all the designing problem, you have to follow the steps for the FIR filter designing. The first step is represent HDN in a mathematical form. This omega is the radian frequencies, remember, and this is the complex form of HD e raised to j omega. Always this is given for the pass band range. For stop band it is 0. Always we are referring the ideal filter in case of FIR filter designing. Then next step is apply the inverse Fourier transform to get the HDN for this desired frequency response. One more suggestion here is you can directly use the generalized formula to get the HDN. Instead of solving the inverse Fourier transform, instead of increasing the computational complexity, you can directly use the generalized formula to get the HDN. Next step is add the shift. When you will get the HDN, it is a sync pulse, infinite in duration and non-causal. When you are using generalized formula, you will get the non-causal signal and infinite in duration. So this is your sync pulse, and you have to add the shift, and shift is m minus 1 by 2. M is the order of the filter, and the next is you have to make it finite by multiplying by window function. This can be the different window functions. Here it is rectangular window, but window function can be Hamming window, Hanning window, Blackman window. Like this different window functions we can use to make it finite. And the last step is plot h of z, and from that z we have to replace the z with the e raised to j omega to get the h of omega, and this h of omega should match with the desired given frequency response. Then we have designed the filter with the right order. Otherwise, change the order and follow all the steps. Thank you.